right. Yeah. So yeah, we'll go over section 35, which is right. Section 35, ensemble methods. And so this is kind of like we've already at this point, hopefully we've seen section 33, 34, a couple more machine learning models. I don't know. I think this section, for me at least, seems a lot of fun. I think a lot of people enjoy this too. Yeah. So it definitely is a lot of like, it's kind of cool to put these things together. So one thing we've learned already was decision trees. Another one I think that was in section 33 is k nearest neighbors.
Yeah.
So yeah, so we kind of seen some advantages and some differences between those two. They're both supervised learning algorithms. So it means you still have to know basically what your training data, for your training data, you have to know what the label is.
Right.
There's no way to like guess it kind of thing. And this is classically like, classification. So ensemble methods are kind of like an ensemble, like getting like a band ensemble or something like that. Basically, it's many different, we'll call them like learners, basically put together to make a better learner. Okay. So, and I realized too, so I'm going to share my screen first. Let me turn off my notifications. Okay. And share my screen. And then Zoom likes, I don't know what Zoom does. Every time I share my screen, Zoom moves all the windows all around, so I never find them right away. Okay, so so this notebook I'll go through, and so Rachel, since I haven't had you before, I just want to let you know that you can find all of this notebook. I sent you the link on the Zoom chat, but you can also, if you go into GitHub, you can find this particular notebook or whatever notebook I have. This is what I use for all my, like if I do like lessons, like, study groups. So in this case, it's actually going to be in machine learning. I try to do it by subject and then ensembles. And then this might actually be a little outdated, so I might actually have to update this afterwards, but the notebook will all be in here. Okay. So.
Great, thank you.
No problem. All right. So why an ensemble? Why does this work? Well, I like to think of it like, I don't know if you're familiar with like Captain Planet. Like, I used to wake up all the time, like at 5 in the morning, just to watch this as like a kid. Like, it's kind of ridiculous. But, if you know, it's kind of like Power Rangers, like, but like a little lamer. I don't know if lamer is the right word, but like they were about like the environment and stuff like that, and they each had like a different ring with a different power. I don't know if it's starting to sound familiar at all, but they all have like a different power. Like one's like earth, one's like wind, fire. I think the one's like heart, which is like no one knew what that kid did. Like it's just like, oh, what can you do with your ring, heart? Okay. But the idea is like they all have these separate powers, and their powers combined. Summons like Captain Planet, which is like the superhero of like eco-friendly kind of stuff. Yeah, so I don't know if you ever heard that. If you look at like Captain Planet memes or like the theme song, it's pretty catchy. But anyway, this is kind of like what an ensemble really is. We're basically taking a bunch of different learners, and the way we say different learners, they can be different. Essentially, they can be other models, right? So other machine learning models, for example, we'll see in decision trees. We'll actually combine these together, and the reason why we use ensembles is that we basically decrease this variance. So we actually decrease the chances of overfitting. It's actually really awesome, especially like decision trees, which you'll see a lot usually in what's it called, ensembles. You usually don't see decision trees in it in most circumstances by themselves because going through the curriculum, what is the big issue with decision trees? Or actually, it's biggest.
Well, from my perspective, it's like really hard to tune the parameters, and it's, if you don't tune them, it just becomes, a gigantic tree, and it's overfitting.
Yeah, that's the key part, the overfitting part, right? And you have to like tune the right parameters and see exactly what you should use. Sometimes it's like, oh, I shouldn't use this feature. I should use this feature. How many minimum number of samples per leaf and such, right? So, but the big part, the reason why you have to adjust those parameters is for mostly overfitting. Decision trees love to overfit. They like to make everything very like defined. So it turns out ensemble methods kind of help avoid us doing that overfitting, which is a lot common in decision trees. So I realize, I don't know why this is first. This should actually be second. So I must have changed this. Well, okay, that's fine. Well, skipping over decision tree random forest. There's a few ways we can do this. So there's bagging. So this stands for bootstrap aggregation. Random forest, which is talking about like decision trees. Adaboost and gradient boost. Gradient boost is a more advanced technique kind of deal where we're using with a gradient descent and such. Boost. So we'll talk a little bit briefly about this and how to implement it. But the simplest one is basically this bagging, also called bootstrap aggregation. That's what it stands for. It's the B in that AGG. So your references as backing. So the main idea here is that you take a bunch of what we call weak learners, right? And this is directly from the curriculum, if you recognize this picture. Basically, you take a bunch of weak learners, you combine them together, and you say, cool, this is like all of my different people, and you essentially have those guys all pick these different, what's it called? These different learners vote together. And the idea here, I think the curriculum uses the word like wisdom of the crowd. You ever heard that? Like for ideas like Wikipedia, anyone can edit it, or at least mostly people can edit it. And the idea is that, you know, for generally you can get some consensus going on there. That's kind of the idea here. I don't think it's the perfect analogy because it's not quite the wisdom of the crowd. It's kind of just like using a lot of different parts. Because remember, bootstrapping means essentially random sample with what's it called, replacement. So essentially what we're doing is basically combining these parts by taking a random sample for each part, and then we take those parts, feed it into our different models, and then with those models we can actually get an aggregated model or bagging model, right? So this is kind of like a theme that you'll see pretty much for these other ensemble methods and all that stuff. So the most famous one is probably random forest because it's relatively like easy to understand. It's a high performance, so it does really well with like basically low variance and stuff like that. You're less likely to get overfitting. It's relatively transparent, which some machine learning algorithms just have a real hard time. For example, I'm thinking of like deep learning, which we'll talk about, like, you know, in like, was it module 6, I think now?
Yeah.
So yeah, they renamed the numbers, so it always throws me off. But yeah, deep learning, like where you don't really know, sometimes it's referred to as a black box. You're kind of like, you get an input, you put inputs, you get an output, and you're like, I don't know what's going on. And that's kind of like, well, like we can't really see. If you try to open up that box, it's more or less not really certain what's going on. A decision tree is really easy because it's kind of like, oh, it's either yes or no, you know, yes or no, all the way down. So random forests actually inherit that kind of transparency from decision trees. So these will actually be used very frequently. A lot of times people like will try to do it, like the joke sometimes for data scientists, like they'll try some really advanced method and they're trying all these things, and they should have just done a random forest, which would have been just as well. Sometimes it's just better to do it this way. And again, they're usually a lot easier to understand of what's going on, what's happening. So yeah, and I call it like the super friend. It's kind of like, you know, you're summoning like your superhero friend. Basically, you're getting a bunch of people together and you're making one super friend that knows a lot of different things. Okay, so, and the important part is that we're doing it from multiple trees, hence forests. You know, I think that's kind of clever. And so you can probably guess the random part. It's from randomness, right?
Random sampling.
Yeah, so we'll actually talk about like where this comes from. It actually comes out not random well, it's part of it's from random sampling, but most of it's actually come from randomly creating different trees. And so we'll talk about like why you have to create different trees, and that's the important part. But yeah, part of it is actually getting different data too. Okay, so and yeah, so some bads though is that you have to have a lot of trees. And so what happens there is basically two things. One, it's computationally expensive for you to actually create all these different trees because you have to basically make a decision tree every single time, and you have to make many decision trees. Okay, so it's not just simply one. The memory too means that you have to store all these trees. So sometimes this is not a big deal for some models, but if you are making a model, which sometimes like what we'll do is you can develop a model on your computer or a larger system. It takes a long time, a lot of computational time to actually figure this out. And then at the end though, you get a relatively small model and you can pass it on to like your phone, you know, you can pass it off to like something that's relatively like limited with memory and such. However, random forests, essentially what happens is you have to store all the trees and you have to store like basically how each part gets split up. So it's not just one decision tree, it's like many decision trees with many decisions. So it just takes up more room. If you think back, yeah, go ahead.
So it's like hard to run inference on like edge device.
Yeah, if you have something on the edge where it's like, okay, like if you have limited amount of memory, think of like if, I don't know if you're familiar like with the Arduinos and like Raspberry Pis, some of those like smaller items, like where it could use that kind of putting in the features, it has to store that whole information, which might not be a huge amount considering like our modern computers. Like it could be like, I think the curriculum talks about like 100, like a few hundred, you know, megabytes, which is like relatively small. But if you're trying to give that to a device that is limited on storage space, then that starts becoming like a big issue where now you have to beef it up in order to get more computation part. So there's other algorithms, other machine learning models that we can basically, they tend to be smaller. So one things like that happens are like deep learning algorithms can actually be very, very small, as they're very, very efficient. But at least with this, it's relatively easy for us to understand in like developing it and also testing it out and debugging it. So we can see like, okay, what are the decisions it's making? We can actually plot this out and see what those things are. Okay. So yeah. And then you can think back like to k-nearest neighbors. The same issue kind of is there. I don't know if in the curriculum you kind of caught it, is that in k-nearest neighbors, it talks about how it takes up a lot of space because it has to know your training basically is just all the different data points. So if you have a very large data set with k-nearest neighbors, it's going to take up a lot of space on whatever device you put it on. So you have to keep basically the whole data set. Something similar is happening here is you have to keep all decision trees with all of their decisions. So it can be a little more like cumbersome.
Yeah.
Cool. All right. So those are the goods and the bads. But generally, like if you want to do good, it does pretty good performance-wise, and it's really transparent. So it's nice to have. Okay. So the way we actually want to do this is that we use something called subspace sampling method. And what's happening here, and just kind of like leading into like, what is this going on? So I say, don't be like a banana tree. So I don't know if you're familiar with bananas, anything like that. But there's actually bananas, you know, those bananas that you eat, you know, go to the grocery store and stuff like that. Those are all actually one type of banana called the Cavendish banana. And the Cavendish banana is kind of an interesting one because it wasn't the original banana. There actually was a banana before this. And actually turns out bananas can be very susceptible to Panama's disease, which, you know, this is like, you might be like, what are you getting at? But the idea here is that when one species of tree, of bananas, basically get this, it spreads really, really easily. So it turns out when you do this, like every time you eat a banana, like modern day bananas, they actually are all clones of each other. They're exactly the same. So if one tree gets that disease, it spreads very quickly throughout the whole bunch. Like they literally like burn like these fields of trees to make sure Panama's disease doesn't come through. Okay. And it turns out, this is a little history lesson, turns out there was actually another, the banana, I can't remember, I'm forgetting the name off of the top of my head right now. I think it's called I don't say something, the Michael's banana or Michelson banana or something. But it was a sweeter banana. It was actually a better tasting banana than we have today. But it suffered that same fate. So kind of fun fact, you ever eat like artificial, like if you eat a little candy that has banana flavor, like artificial flavor, usually it like doesn't taste like a banana. It tastes good, but like it's not a banana. It's actually based on that other banana. So anyway, the point is I'm trying to get at is you don't want all your trees to be the same. Okay, basically you don't want them to be clones because our Panama's disease, which is basically our overfitting. Okay, the problem is that we're going to have the same result. So it turns out decision trees, our decision trees, if you give it the same data, it will give the same exact tree. And do you know why this might be? There's a special thing about decision trees. It starts with the letter G, but the reason why it might have this issue.
Because it's selecting the entropy, like a criteria is the same.
Yeah, I think you're getting it. That criteria is the same, which is the entropy information gain, right?
Yeah.
And we have, we call it a greedy algorithm. So it's like,
right.
It wants the best thing in that moment. Well, the thing is, if you give the same data, it's always going to choose that one thing. It doesn't do it randomly. It's very deterministic. So if you give the same data, you're just going to have a whole bunch of trees, a whole bunch of clones, right? And you're susceptible to Panama's disease or overfitting here. So we want a variety of trees. We want a huge, you know, different swath of, you know, different bananas and stuff. So Panama's disease doesn't get to us. So, and that's what subspace sampling happens. So there's some steps right here. I'm just kind of walk through them a little bit. But basically the idea here is that we're trying to create different trees and combine them together. So essentially what we do is that we have a whole bunch of data. So I'm actually going to draw this little guy over here. Cool. So let's say we have like this whole bunch of data going on here. And so this is a whole thing of data. Think of it like, you know, our pandas thing. It has a bunch, all these rows, each are a data point. We have a bunch of columns, right? And so essentially what we'll do, we'll just essentially take out half of this and say, okay, save this for essentially validation or testing. So this is called like the out of bag part. So this is all for validation. And then inside of here is all going to be our, what's it called? Our bag. So this is the stuff we're going to use to train. And so I think the curriculum talks about 2/3, you know, keeping 2/3 of it for training and then 1/3 of it for validation. You can adjust those ratios. It doesn't have to be those numbers. But usually you want more training than validation, because if you have more training, it means that you can actually do better on top of those things. You might do things like you could, like, for example, we talk about K-fold and stuff like this, cross-validation. So this is our bag right here, and that's what we're actually going to use to train. Okay, and so you can think again like this data as essentially as a bunch of rows. Like if you think of like a pandas data frame, we have all our columns, right? And then we have like all of our rows. Like, so you can have like, 2/3 of the rows. So like, I think the curriculum talks about like 2,000 rows. So this is what we'll train it with. So that's our step one. Cool. We basically save a portion of it out of bag for validation. The rest is for training. Then we go to our second step. The data for training bag, the data for training is then split up by randomly selecting each predictor. So predictor, it's just a feature. That's really what we're talking about here. And so, for example, if I want, I say, okay, randomly select it, and note that we don't pick the same feature twice, which kind of makes sense. You don't want the same feature again and again. So you're going to use this whole data set, like all of it, but you're only going to pick like this column randomly, right? This column and maybe like this column. Okay. And so you decide how many predictors or how many features you want to use for your decision tree. Then all you do is say, okay, that's my new decision tree. And now it has, all of the rows from, at least from this bag, but now it only has, let's say, like 3 columns, and those 3 different columns. And then you say, okay, make a decision tree. So basically you take that data and say, make it a decision tree classifier, and that's your classifier there. So that's our step 3. Okay. And so essentially I call it like growing your tree or training your tree. So you're creating this thing now. And all right, you keep that aside. Then what you do, you take your validation, and then you say, okay, using my validation, you're just going to say, we have that tree model, right? We already figured out what it's supposed to look like. We basically, pour in the data down into our decision tree, see where all the data ends up being. And then we take those different points where they end up and say, okay, did those match up with the actual targets? Did they actually go in the right spot? And this gives us our out of bag error. So essentially what's happening is that we design it with the training data. We only select certain columns. We make our specialized little tree, right? And then we take our validation data, our out of bag, apply it through our decision tree, see how well it works. We count up all those errors, and we basically get this error part. And that's how we kind of judge how well it goes. And then we just keep repeating this over and over again using different columns, however you want. So some trees might have, let's say like these 2 columns and then this column, but another tree might have this column, and maybe this column. And then you'd make all these trees. So that's essentially, you're making a forest, right? You're making all these different ones. Yeah. Cool. And so we created all these guys over, you have these different trees. And then essentially at the very end, we just have them all vote, essentially. So what happens then to decide when you have this all created, you created your random forest, right? So you have all these different trees. And then what you do, you take your new data point that you have no clue what it is. You're like, I don't know what this is. Like, I just got it from, like whatever thing. You basically put that data point or your data, and you pass it through every individual tree. So you go through every forest or every tree in the forest. You see what it results in. You're like, okay, we have, let's say 100 trees. You see what each one of those 100 trees says. So you'll have 100 different results, and you basically just pick which is the one that's most common. And you say, oh, the one that's most common, we'll pick that one. So, and that's how you basically use a random forest. Cool. Yeah. Any questions?
Yeah. But how do you know, like, how many trees you need?
Yes. And that is the part that's always a big question. In reality, you don't ever know. You don't know exactly what is the most optimal parameter and stuff like this. And this is where I actually go into my code here. So this is actually from scikit-learn. It's always useful to look at the documentation. At least that's what I find. So we have our random forest, and essentially you can see all our different parameters here: max depth, criterion, and estimators is basically how many trees we're actually going to put in this forest. Exactly how many you have, it all depends on your situation. And what you might do is actually do a what's it called? An ROC curve, ROC curve. And so you basically would say, okay, well, let me try it with this many and this many and this many and this many. And you see how well it does each time. Because you don't want to do so many that it's basically overfitting. A good rule of thumb is you probably don't want more trees than the number of columns you have. So if you have 10 columns, you don't want to have like 20 trees because basically you're going to be reusing them over and over again. So I think there's might be some example code that actually show down in the bottom here. So you can see here, for example, they have 1,000 samples. It looks like 4 features. Yeah, they're just making up data here. And then they actually pass this through here, and they're just using the default, what's it called? I'm sorry, I might have misspoke. I said like don't use this like more trees than there are features. That's not necessarily true because you can have like, let's say two columns, you know, and 4 features. Well, there's a bunch of ways you can do that. It's like 4 choose 2. So there's going to be more than 4 actual different ways you can combine these parts. Right. But you'd want to be aware of, like, don't put like 1,000. You want to make sure you don't like have a repeat, basically.
Right. Right. Yeah.
Yeah. So, yeah. But exactly like which number of trees you don't actually know. And this actually applies to grid search, which is also in this section. And essentially, you might try, like, I think what I try to do is a little kind of more computer sciencey, kind of a good trick, is you kind of do, instead of just going like what most people might start doing was saying, okay, let me just try to do a bunch of parameters. You might say for number of trees, you're like, or number of estimators, right? Number of trees. You might put like 1, you know, or try out like, let me just try out 1, and let me try out 2, let me try out 3 trees, 4 trees, 5 trees. That's a really slow way to do it, because you have to go through each individual one. So one thing you can do is like, well, what's the most you think we should use? And like, let's try like 25 different trees, you know? It seems like that seems about how many you want. See how well that does, right? And you say, well, let's go at the lower end, like 5 trees. And then you might have like, okay, in between those 5 and 25, like, well, that's like 15 trees. Okay, and then you might have some in-between parts. But one thing I would suggest is try to like half it, because usually that kind of gives you an idea. And this will also help you generate that ROC curve that will tell you what to go through. And this is where grid search, instead of you having to make this function, run it with 25, make this function, run it with 15, and so on, you can actually have it go through all parts. So you can actually say, okay, well, I wanted to have the estimators be, say, you know, 5 trees, 15 trees, let's say 20 trees, and 25 trees. I can't write my numbers today, but you get the point, right? So those are my different parts. And then you might say, okay, well, but with max depth, I actually want to adjust that as well. I want a max depth of like, let's say, I'm just making numbers now, like 4, 8, and like 12. What's cool is grid search will actually do, okay, let's try it with a depth of 4 for 5 trees, 15, 20, 25. We'll do 4 different trees there. Then I'll try it with 8, 5, 15, 20, 25. So it automates this process. Now, it automates it, but it means it still has to do each individual tree. So grid search can take a long time if you give it too many parameters. And this is where you might kind of find a little bit like what exactly is right. And this is the hyperparameter tuning. It's definitely not, it's more of a art than science. Definitely kind of like, I mean, I don't like using that phrasing because it sounds like it's like, oh, it's black magic, but it's not. You would say like, oh, well, it seems to be overfitting. If it's overfitting, I might have too many trees going on here, or my depth is too deep. So you'd want to try to use something that's smaller. And that's what your ROC curve really is trying to do. It's trying to see your false negatives versus your false positives, basically seeing how well it's overfitting or underfitting. So you're trying to find that nice sweet spot. Hopefully that kind of like just generally saying like exactly what it is, but yeah.
It's really helpful. Thank you.
Okay, no problem. Cool. So yeah, hey, you want me to keep going then? Yeah. Okay, cool. So yeah, going back to our random forest then, right? We have our, just what the benefit is, it's just less overfitting. So it means that basically we have less ways for us to, there's more variety. So sometimes it's going to get slightly wrong, sometimes it's going to be slightly right, but it's going to kind of balance out. So that wisdom of the crowd, or like, you know, I think of it like, you know, if you have many different banana species of trees, right, and Panama disease comes by, it might kill a certain species, but you still have another one doing fine. So the idea here is that you have a wide variety of different like learners. Okay, cool. So that's like, and this one I should say like random forest is like a good go-to as being like, hey, like, let me just see how this works. Random forest usually does pretty well. I think a lot of, I mean, I say like Kaggle. Are you familiar with Kaggle.com? Yeah.
Yeah.
So a lot of Kaggle users will use random forest as like a first initial start because it's so just good at that. But you have to be considered, for memory. It's probably the biggest part. So any questions on like random forests or anything like specific about that?
Nope.
Okay, cool. All right. So next one is Adaboosting. So Adaboosting is a pretty like it's a little more complicated than like a random forest, but super like useful too. So basically the steps of like Adaboosting is that you have your data. And this is again taken directly from the curriculum, kind of walking us through. But basically what you do, you make a split and you say, hey, like, what was right, what was wrong. You increase those errors to say, okay, like let's increase the errors that were wrong. So it's more emphasized, and then you make a new split. And then you just keep repeating this over and over and over again until you have the number of splits that you want, or whatever your stopping condition is. So the way this kind of goes through is basically you go across here and you just say, okay, I'm going to split across, and you can imagine the minus being like it should be red, the plus being it should be blue. And you basically, as a greedy algorithm again, so it's like saying, okay, like let's see where we should split it across so that we get, what's it called? Like I'm trying to get this right. Basically, you're making that split across, say, hey, like let's make this so it's got the right information gain. So we have a good amount. And then, so this might not be the best line, but you get the point, right? It's about like half of them right. And let's see here, 1, 2, 3. Yeah, so you can see here, there's 2 right here. There's 5 right here, but there's 3 wrong. So it's balanced out. And then what you do, you essentially say, okay, which ones were wrong? And you can say, okay, well, this one was wrong, this one was wrong, and this one was wrong. So you basically increase that error. So that way it ends up being that there's 50% of the errors on the one side, 50% of us on the other side. So you increase it basically like, how do I say this? The reason why I'm kind of like going over it is because you don't necessarily need to know the math specifically, because basically your code is going to do it yourself. Like you use a package, but essentially you're increasing that error and then say, okay, let me try to redraw a new line. So now you say, okay, completely ignoring this line, let's draw a new line where we want to make sure we get more of these. In this case, we increase the blue right here. So we increase that blue and we say, oh, well, since we want these to be more correct, we actually end up making a line over on this side. So we're basically getting those more correctly. And then what you say, okay, let me increase these errors now. You increase those and start over and basically do that same thing where now these errors are really important. So now we make a new line going through here. And so we basically keep doing this over and over again for a stopping condition, and we combine them together until essentially we have something that's kind of like our super learner right here. Basically, it's a combination of this one and this one and this one together. And this is how it kind of like pulls it all together. And this is kind of like how you would do like a little voting system. I almost hesitate to like show a little bit like the voting system because it's more mathematical, like what's going on. But basically, you can think of it as that the ones that get it really right, they're like the truthful ones. And then there's like the guesser one, which the guesser doesn't really give us much. And then there's the liar, which we actually do want to include because it's kind of my kind of scenario is that if you have, like the way I phrase this a lot is that if you have a friend who's a good friend and has similar taste to you, if they say like for a movie, it's like, hey, what kind of movie should I watch? Like, oh, I really like this movie. Well, because you guys have similar tastes, you're like, oh, I should go watch that movie. So that's kind of like your truthful person. You're like, oh, you know what you're doing. Now, if you have a really like, maybe not a friend, but maybe like someone who's like completely different taste from you, and like every movie you love, they hate, and every movie they hate, you love, like that kind of deal. And all you gotta do is like they go and it's like, oh man, I hated that movie, and you say, oh good, I should go watch that movie. So your liars actually give you a lot of information. So you do want to basically, versus if it's like a 50-50 chance, you're like, oh, you give me no information. That's why we kind of rip some of these at zeros. And essentially what we do, I'm going to just go through this quickly, basically, is you take the accuracy of each of these learners, you take the logarithm, and then you get the log odds of these parts, and then you use that part to calculate, what's it called? You calculate how you should combine them together for each crossed area. So like, this is kind of like how you build this part. It's definitely a little more involved algorithm than a random forest. Random forest is a little bit easier to do. Adaboost is a little more complicated, but in the end, like to be honest, it doesn't matter for you completely to explain like it's like what's the exact code or what's the exact mathematics. You can of course look it up and like see what it does. But for the most part, you're like, okay, if I understand that concept, then you can actually like create this. And for example, this is a really simple like how we would do an Adaboost, assuming you already have X train and Y train. And essentially that's all of the code you really need. So you can kind of see here from sklearn is that we basically can do our different parameters, a base estimator, our n estimator is basically how many times we should try to repeat this stuff. Our learning rate basically is kind of saying like, you know, how much it should contribute to each time. So that's kind of like if you're boosting up the error or decreasing the error kind of deal. And then there's other things you can do, for example, like loss function and say, well, what should you do? But the idea here is that in the end, you end up just importing this Adaboost and classifier, and you can go from there. Oh, I think I actually put regressor instead of classifier. So I think I've actually changed this too. Actually, classifier, I didn't say no. Here we go. So you can see here now is that this is the actual code you would use probably. So essentially what you're doing is like, okay, put in this in. And you'll notice this random stake here. This is considered like best practice because you can reproduce that same learning and like your same model every single time. Because it is kind of random, but we want to start off with a seed. So that's where this comes from. But yeah, that's kind of Adaboost. So it's kind of like, again, just another way of doing Ensemble where you have different predictors, or some predictors, I guess predictors, estimators, and they combine together to make one super, you know, friend. Cool. All right. You have any questions?
So how does Adaboost compare with the random forest?
Yeah, actually, Adaboost does really well. And what is nice about Adaboost is that it doesn't take up as much room, like compared to random forests. Like because on here you're like, oh, well, I have to remember each individual, you know, estimator. But all you need to know for the estimator is basically that cutoff point. So versus a decision tree, you have to remember all the points that it flares out to, and then remember that for each one. With this one, basically you just remember a cut. This cut can be in hyper dimensions, right? It doesn't have to be 2D. It could be like in 3D and 4D and all that stuff. But essentially just remember the cut, and that's relatively small to store. And then you just combine them together.
Yeah.
So yeah, cool. And then it's just hyperparameters, like I mentioned. You can basically do some really cool, interesting things. So when you make that cut through it, you can actually decide to use, like, for example, another algorithm, for example, a decision tree. So you can actually pass a decision tree to say, hey, we call these like weak learners. We say, weak learner, go ahead and figure this out. And then we would repeat this algorithm to figure out where that cut goes. Like, for example, we could use a decision tree to decide what that cut is. And then we increase these like errors and stuff like this. So that way we can rerun the decision tree or whatever estimator we use to do that. This is why I'm not quite sure why it's called Adaboost, but in my mind, when I hear boost, it's kind of like, oh, it's like boosting up any classifier you already started off with. So yeah, cool. Yeah, so sound good?
So does it matter what weak learner I pick?
It would matter because if you're weak learner, for example, if you're weak learner, which is random guessing, it'll never do very well, right? So it would matter which kind of classifier you use. The good thing is that decision trees are relatively fast and quick. And so sometimes it can be a lot quicker in how to, like if you wanted something that's a certain part, another version of this, I think this is in section 36 coming up, is support vector machines. Sometimes you would pass in a support vector machine into this base estimator and stuff like that. And the idea here is you want something that's like, you want to essentially increase the you want to improve a classifier that you already started off with.
Right.
So one thing you want to do is you probably wouldn't put in like algorithm or machine learning algorithm classifier that would be really complicated to do and then like try to pass into Adaboost, because then Adaboost would have to perform that complicated one for each one, and you might not get that much more benefit of it, if that.
Got it. So basically, nicer, fast, but not too complex as a base estimator. Okay.
Yeah, and that's where like decision trees and support vector machines, those are the most common ones to use. You probably, I don't think I've ever seen anyone actually put in like a random forest in there, just because then you would have a random forest to predict on an Adaboost, and like I don't even know necessarily you would get that much more benefit from it. Right. So that kind of helps you like put it. But honestly, since you're kind of like trying it out, try things out, see what happens. Like kind of see if you can see a difference between different estimators. But generally, we'll use like what we call weaker learners, but basically ones that are really fast, but might have some issues with like overfitting and stuff.
Right.
Cool. All right. Awesome. Yeah, so that's Adaboost. Again, it's just another way of applying an ensemble method. So our last one to kind of talk about is gradient boosting. And so this one, I'm not going to go through the whole algorithm of it because it's basically through gradient descent. I do have it written down here, but like it's not super important. But the important part, at least the conceptual part, is essentially we're doing the same thing. We're improving it each time, but instead we use gradient descent to figure out how we should improve it each time. So basically, this is again from the curriculum, you essentially take the residuals for each part and you keep improving the model by incorporating the residuals. And so the idea here is like you take, so you imagine your first model and your residuals like are just awful, like really bad, like really high residuals. So then what you do, you model on the residuals, say, well, how can I make a model that would fit well on these residuals? Then you basically apply that into your original model. You apply those together to create a new model, and then you look at those residuals, say, oh, this is still kind of high. For example, you can see here's with the new model, or sorry, here's the new residuals, and then it applies. I'm sorry, this is the same residuals. This is the actual model itself, I think, and then this right here would actually be the residuals from that model. And so we combine that. And we say, okay, these are the residuals. Let's model off those residuals, and we improve a little bit better. And it's like, well, our residuals are still kind of off, so you model on top of that. And then by modeling on top of that, and you keep incorporating it into your original model. And eventually you get smaller and smaller residuals. So the reason why we're able to do that is basically through gradient descent, where you're trying to minimize that loss, which in this case would be something along like the MSE. So your mean squared error, how far is it off, which is really what your residuals are talking about. Okay. So yeah, that's kind of like basically what's going on. The important part is to realize that we're using the residuals, basically how far off is it, that MSE. Basically, is there a pattern there, and can we create a better model? So the way this kind of looks like is that you can imagine our F1 being like our first model. So our F1 is our, let's say our green model. There's our green model. I guess that's whatever. No, I guess this is the ground truth. I'm misreading the curriculum stuff. This is the actual like what it should be. And then say, okay, well, let me make this model that's this blue right here. Say, oh, that's not really that good. And so you take that. It's like, well, we find H1x, which is our residuals. And that's just simply saying what the ground truth is, which is y minus F1, your first model, and you'll get your residuals. And then what you do is like, well, okay, let's create a new model, F2, that basically incorporates your first model and the original residuals. And then you keep passing that over and over again. And the idea there is that you get essentially a better and better model. This is more conceptual than like actually what you do. You wouldn't just simply say, oh, just put this in here. Because obviously if you put that in there, that's just literally just putting the ground truth, right? So like that one, like, but the idea there is like you're doing an estimator every time using gradient descent. And again, a lot of these algorithms end up being like, do you need to know the full complexities of how they work? Generally not. The important part is to understand where they are so you know when things go wrong, how you can fix them. So this is our gradient boosting classifier. You can see, for example, our learning rate that's related to our gradient descent. And going further, you can see there's a whole bunch of parameters you can put in. But in the end, you end up getting, let's see if there's actually example code that I can show you. Nope, there's an example code. But the same idea here is you create that sklearn.ensemble gradient boosting classifier. You basically define that, do a fit, and then you can perform on it. So yeah, not too bad. So this is a really powerful method. And then the last one, I didn't actually have anything written specifically for this, is XGBoost. XGBoost is kind of like taking gradient boosting and it does a lot more to it. So like if this is like, it's like, oh, this is me conceptually explaining it. Gradient boost even has more aspects of it. So to be honest, to try to go through it and say exactly like, why does it just do so well? It's just easier to just like, yeah, it's a better algorithm that does boosting, but it has some extra features that are going on here. And this is something that's used quite often in like a lot of data science competitions because you essentially can keep improving it. And so, yeah, so this is kind of like, if you were to kind of like rank these down, be like, oh, like what are the like tend to be the most powerful? Random forests tend to be like the most quick and dirty, just like, all right, let's make this work. After random forest, you really would get into like Adaboosting and then gradient boosting. And then from gradient boosting, there's actual code for XGBoost. So you would import XGBoost and use that from there. And yeah, that's kind of like your quick and dirty, like, you know, machine learning parts. But it's really nice because they're Ensemble, so they actually like, what's it called? Like, because it's kind of cool because it means you don't have to like make this one really great model. You just get basically like these models that are decent enough and combine them together. And you will see this kind of concept if you ever get into things where they're playing off of each other. So like the one that comes to my mind is something called generative adversarial neural networks, or GAN. If you ever seen like on like a little bit of like kind of pass around where like they have, for example, one of them is like they convert a horse into a zebra, a picture of a horse into a zebra. I don't know if you've seen that one before. Or if you've seen like, there was one recently where like they had pictures of like, you know, like said the Mona Lisa, and they were able to like make it like the mouth move and stuff like that.
Right.
It's kind of like, it's not this, but like the idea that it's playing off of another machine learning algorithm. So they kind of improve each other. And so you're kind of like not using just one, you're actually using multiple ones essentially to help improve. It's not exactly, maybe not the best analogy, but I think it's kind of shows a little bit like how useful these things can be. So yeah. But that is overall is Ensemble. So yeah. Do you have any questions on bagging, random forests, Ada boosting, you know, gradient boosting, anything like that?
Nope, this is great.
Okay, awesome. Yeah, hopefully it's more like, it's definitely more conceptual, but I think it's important to like say, okay, like understand what these parts are, you know, say what they are, and then actually be able to code them. Most of the time when you're doing like modeling, the hardest part really is doing the data stuff. The data part, the data processing, the data cleaning, you know, making sure everything's ready to be passed into a model. That's the first step. The next part after you kind of do that is you just feed into your model. Well, it's just figuring out what, like you said before, what parameters should I use? And he's like, yeah, that's a good question. And it definitely is a lot of work. And this is why you would, like, if you were in a professional setting in a, especially a big company, you might use a parallel system, a distributed network and stuff, which I believe is talked about in this section. It is the section with PySpark. That's section 40, I think, when I talk about distributed systems and stuff. And that's where you would say, okay, let me do a bunch of different models and see which one works well. Because it's a little bit of like saying, well, what exactly should you do? It's like, well, it depends on the data, and it's hard for us to know exactly which ones to start off with. Right. But as you get over time, you kind of get a feel for saying, well, this data tends to be structured a little bit better, so I think random forest will be fine. It's a little more like loose. You might say, well, you can do something closer to XGBoost or other, what's it called? Other machine learning algorithms and such. So, yeah.
Great.
Cool. All right. So I guess I'll stop it here, recording. So.